Okay, so welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very lucky to be joined by Sona Hosseini, who's come across to us from UC Davis, where she's just about to complete her PhD. Sona did her Bachelor's of Science at Isfahan University in Iran on exoplanets. She did a Master's also at the same, in Iran on exoplanets, and then came across to do her PhD at UC Davis, where she has worked in Engineering and Applied Science Division there with Walter Harris on the Tunable Spatial Heterodyne Spectrometer. Sona's interests revolve around astronomical instrumentation, sky brightness and light pollution, and interferometry, and also planetary science. She's the AGU student representative, involved in the student representative class, and at SPIE she's the chair of the Future Leaders board, and she's also involved in next year's 2015 International Year of Light. So today she's going to talk to us about her work at Davis. So please join me in welcoming Sona.
Thank you, Adrian. Okay, well, thank you everyone. It's lovely to be here, and as Adrian said, I'm going to talk about an instrument that I designed and built for my PhD program at UC Davis. I was officially in UC Davis, but I spent almost all my time, or most of my time, at Mount Hamilton Lick Observatory. And I'm just going to walk you through why I built this instrument and how I built this instrument and what does this instrument does. A little background about why I picked such a project was I really fell in love with astronomy when I was extremely young, 7 years old, 6 years old, and I was like, this is what I want to do. And then I got involved with astronomical research in junior high, and it didn't take me very long to figure out I was not a person of theoretical physics nor just an engineer. I wanted to do both. I really wanted to design and build my own instrument and do science with my own instruments. That was my goal. So I was very lucky to find my advisor at UC Davis that we worked on a project together, so I could design and build a small instrument, but I did everything by myself. I did the mechanical design, machining, optical design, and as well as the data reduction pipeline and the science that can be done with it. So here it is, a tunable reflective spatial heterodyne spectrometer. I named it Khayyam at Lick Observatory. So in astronomy, usually the hype and the really cool things are surviving and going around big telescopes. Larger telescopes, larger apertures, the better the science, the higher the resolving power, the higher the étendue, the higher the sensitivity. That's what we are about. We would like higher sensitivities for a very good reason. But it's not all about the telescope. It's also about what goes behind the telescope, the instrument. Different instruments, we don't have the best instrument. Different instruments address different science, different objectives. It's like cars. We can't have a best car. You know, a Ferrari works what a Ferrari does, and a truck does what the truck does. So interferometers, spectrometers, cameras, imagers, they're different instruments that addresses different sciences. So let's talk a little bit about what goes behind these telescopes. We want a higher sensitivity. And then there's a good reason for that, because there's really good stuff happening in the astronomy that higher sensitivity would help us to gain more information. One of them being Io-Plasma Torus. It's this beautiful torus around Jupiter. It has high energy ions, electrons. It's just gorgeous. But if you want to look at the entire torus, we don't have a spectrometer to look at that extended target in the sky. It just turns out most of our instruments and spectrometers and interferometers are built to gain high resolving power at very small field of views. They're conventional grating spectrometers. So people, in back of their mind, they think, oh, okay, so if I want to go to higher resolving power, my field of view has to drop. Or if I want to go to wider field of view, my resolving power has to drop. It's the sensitivity balance. So what turns out is, if you want to look at the Io-Plasma torus, we can't have the torus in entire one slit. We can't look at the spectra of the entire thing. And if we do, we're overlapping the data, and we're kind of abusing the instrument and our science data and complicating the data reduction pipeline to get the spectra from wide field of view. So questions like, what does this torus comes from, would benefit if we had a chance to look at a very small portion of the torus, or even a larger side of the torus. Or what if I could study the entire torus? What if I could get one high resolving power spectra from this entire object? Well, if we could, then it would be easier to answer where these torus comes from and what are the interactions between the electrons and ions. Or another thing, we have Venus and the night glow on Venus. Very tiny emission lines, weak, challenging. It would help us to get higher sensitivity. It always helps us to get for getting higher resolving power spectra. But Venus is extended on the sky. These things, you know, when we talk about astronomy, people usually think these things are small. Well, they're small, but not in the scale of 1, 2 arc seconds. They're extended. They can be 30 arc seconds, 40 arc seconds, 55 arc seconds. So what if I had an instrument, just in your imagination, just let's fantasize, what if we had a spectrometer that we could get about 100,000 resolving power from that entire space on Venus, from the night side of the Venus? Well, given it's a very hard intensity contrast over there, but what if we had that instrument? There's a different science that we can answer if we had these instruments. I'm just laying out what kind of instruments are available. And these are the things that we cannot do because we don't have the instrument. So you might have guessed, I'm targeting a specific targets. I'm targeting diffuse extended targets that are low energy, they're faint emission lines. And also, looking at solar system targets, these things can temporarily change. They can change within hours. If you're looking at Venus night sky or night emission lines, or if you're looking at comets, or if you're looking at solar winds, these things change on hourly or minutes. So we need an instrument, I'm just saying, we need an instrument that goes wide field of view, high resolving power, and I kind of can use it every night, preferably, for a very long time. So if I can do it, then I can look at the extended targets in solar system and also outside solar system. Again, I'm emphasizing targets that are extended. Any targets like Moon, Jupiter, Venus, even Saturn, definitely comets, some galaxies. If you want to look at the entire galaxy and get one shot a spectra from this entire galaxy at high resolving power. These things, they're not 1 arc second, they're not 0.1 arc second. I was looking at Rosetta's slit sizes yesterday. They're not 2 arc second. They're 30 arc second, 40 arc second. So if you look at here in Jupiter and then after next night you look at there, it's different objects changing. Well, we can argue how much things are changing, but the point is our instruments would not allow us to go better than that. So what kind of instruments are available? Here what we have. For high resolving power, about 100,000 resolving power. So I talk with instrumentation people and scientist people, and they say, we have high resolving power data. Yeah, how much wavelength spectral resolving power? 5,000. Well, that addresses a specific science. How about 100,000? And then large étendue, we tend to build larger telescopes and couple them to the grating spectrometers to get as much photons as we can get. But for temporal studies and wider field of view capacity, people have been using Fourier Transform Spectrometers for years. What I'm arguing in here, the scenario I'm trying to lay out is to match the small telescopes for temporal studies with large étendue and large field of view. We kind of need something between all of these to get the results from high field of view and high resolving power. Because everything we have so far seems like to be perfect for astrophysicists, higher resolving power at a small field of views, and then planetary science people use mostly astrophysics instruments to look at their targets. So what we have again? We have 10-meter telescope, high-res. It goes about 48,000 resolving power, but if it wants to go to 48,000 resolving power, the field of view drops from 11 arcsecond to less than 1 arcsecond. We have McDonald Observatory. We have all different high resolving power spectrometers on 8-meter telescopes, on 10-meter telescopes, and all of them have this nice to show the spectrometers. They go high resolving power, 40,000, 30,000, 60,000, even 98,000. The resolving power is 2 arcseconds, 3 arcseconds, 1 arcseconds. And then if you pay attention, I have a different column over there, étendue. Now what's étendue? Étendue is the sensitivity of instruments. The higher the étendue, the better. It shows the power of the instrument, that how much photon it can grasp. It's as simple as that. So you can see the 440 étendue on Keck is definitely better than 180 or 55. Now, by end of my presentation, I'm going to put the étendue of the spatial heterodyne spectrometers in respect to these, and then you can compare them. So it doesn't matter which telescope, how it does. The étendue just shows how sensitive my instrument is. And then something else. Well, let's just say we are happy with our 10-meter telescopes, with having 48,000 resolving power, 96,000 resolving power over a small field of views. These instruments are gigantic. They're big. That's my car at Lick Observatory, and the shape behind it is the hemisphere. The same size of that room is inside the ground. We can't send these things to the space, not yet. They're just big. So what we're looking for is I'm just making it even more challenging, as if it wasn't challenging enough. I want something wide field of view, high resolving power. I can use every night. And if it's a small, I can send it to a space. That would be really cool. So let's see. Yep. So I want something to look at large targets like comets, because they're my favorite objects in the sky. Nothing can get more beautiful and complicated than comets. And then I want to send my instrument to the space, and I like to study it every night. Just imagine if you had this instrument and you can look at a comet at wide field of view, high resolving power, as if it comes inside the solar system and goes around the sun and go outside every night. That's like a dream come true for a planetary scientist. Okay, so I am here to tell you I may have a candidate. This is a picture of a heart of my instrument. It's this big. It's all reflective, so it literally works in every wavelength. There's no transmitting optics to limit the wavelengths or the bandpass. And this instrument can get about 100,000 resolving power over half a degree field of view. How it does it? Well, let's see. So I have one. I'm not going to go into the technicality of the instrument and the design, but just to show how things move inside the instrument, I have one grating. Now, the place grating, usually gratings are placed for a specific wavelength. This is a symmetric grating that light comes in, diffracts to 2 orders. I take 2 orders, I reflect them off from the mirrors, and then it goes to the grating for the second time, for the second diffraction. Then it comes out. For one wavelength that I counted the heterodyne wavelength, everything is symmetric. I have no path difference, no phase difference, no optical path difference. I don't have any fringes. And I call that the heterodyne wavelength. It's the wavelength that my instrument is tuned. However, for other wavelengths, now this is the cool part, for other wavelengths, depending on how far I am from the first wavelength, I have a phase difference. There's no path difference, there's a phase difference. The wavefronts come in and they rotate in respect to each other. And depending on how much is that phase difference, I get fringe frequencies. That's my data. So depending on how much fringe frequencies I have, I can figure out what's the difference from the first wavelength. So my data are a set of fringes, are a set of interference fringes. And for every emission line, I have one set of fringes. If I have one emission line, I have one set of fringes, and 3 emission lines, I have 3 sets of fringes. And by Fourier transforming, a 2-dimensional Fourier transform of these fringes would give me the power spectra. Yes, this technique can go wide field of view, high resolving power. So I said I have one flat mirror, grating, and a roof mirror. A roof mirror is simply 2 flat mirrors that are glued to each other. It's not a cat's eye, it's not a cube corner, it's a roof mirror. All it does is it acts like a flat mirror, but then the light comes in, it just shifts the height, brings it down. So I can take the beam and put it in my camera. If I don't do it, the light is going to go out in the same direction that it came in. So I'm just going to do a little bit of calculation on étendue. So Hubble does about 0.2 times 0.9 arcsecond. SHS in the other way, half a degree field of view. It's minimum. The real number is about 10,000, but it's minimum. 1,000 times higher sensitivity than a STIS. And it's a small. It's a new thing for new sciences, if you're interested in. But it has a catch. What's the catch? Well, we have wide field of view, high resolving power. Something must be missing in here, the bandpass. And Hubble and initial spectrometers, they have this gorgeous wide bandpass in one single shot. SHS cannot do that. SHS instruments are inherently wide field of view, high resolving power, very small bandpasses. From 5 angstroms, I can go to 1 angstrom bandpass, to 100 angstrom bandpass. So at other instruments, what they do is they have high resolving power and a small field of view, so they scan on the image. They take a little bit of a spectra in here and a little bit of a spectra over there. They come down, they scan on the image. I scan in the bandpass. Is it a good thing? Of course it's a good thing, for whatever I want to do. Okay. And then you put it in next to the other instruments. It's a small, it's all reflective, common path interferometers. It has the most favorable tolerances for temporal changes and other things. This one can be sent to space, but look at the other ones. Those holes over there are 1-inch holes. It's on the optical table. So, enough about how the technique works. This is my baby at Lick Observatory in Mount Hamilton. I've been working on it for the last almost 4 years. I can't believe it myself. It's in the laser pool in the basement of the 3-meter telescope. This is the same laser pool that was used for Apollo 11 mission for the laser ranging experiment on the moon. So they had the laser in here, and then it was sitting exactly on top of that milling machine. And then it was in a pool that they would pour water in it if it gets too hot. And then here I am after 40 years. And this is also the same place that Charlie Towns built his instruments. He put that milling table over there until I talked to him and then said, thank you for putting that milling table over there, because I built my instrument on it. So yes, I went to Lick Observatory because I built the instrument in the lab at Davis, and I was like, I don't want to end my PhD with getting lab data. I want real science data. So where to go? I Googled it. There was this observatory, Mount Hamilton, Lick Observatory, near enough to UC Davis. My advisor was kind enough and very supportive for me to go there. And then I went there, I talked with the director, and he said, come in. So I went there, and I looked for different places to build my instrument, and then we were in the dome of the 3-meter telescope, and it was, I can't work there at nights. I would make light pollution for others. So we went one level down. It was in the slit room of the two, shared focus of the 2 telescopes. It wasn't enough space. So we kind of did what's underneath. We went underneath. It was this junk place. It was a storage. No one had used it for 25 years or 30 years. And then I said, this is good for me. I cleaned up their storage. All those tiles were black. They're white now. And there's also no mice and other things. So, and then the instrument has evolved a lot. It has changed a lot because I had to bypass the guiding camera. I had to bypass everything that the observatory could have offered me, except the Coudé Auxiliary Telescope itself, and then design it myself. And also having the milling table over there, it helped me to just put my instrument on a nice 3-axis, solid optical table. So how the instrument works, I mentioned it's in the basement of the 3-meter telescope, but these 2 telescopes share a focus with another Coudé Auxiliary Telescope. So the story was this beautiful instrument, shell Hamiltonian spectrograph, the one that I showed you behind my car, that was doing nothing when the 3-meter telescope was using the other instruments. So they built this tiny 60-centimeter Coudé Auxiliary Telescope to use it on the Hamiltonian spectrograph. So the light comes in, hits the siderostat mirror, the second siderostat mirror, then it goes to the Coudé Auxiliary 60-centimeter telescope. And then it comes down to the basement where my instrument is. So here, the light comes in, it goes up there. This is the shared focus between the 2 telescopes. This is the hole that Charlie Towns put there. And there are 2 others that I don't use now. But then the hole, if I pick the lid up, takes the light into the basement, to the pool. And then I guide the light in the pool, to go through my instrument. So I pick it up with a flat mirror, and then I collimate it on my grating. There are 2 diffraction orders. It reflects off from the mirrors, and then it goes back on the grating for second diffraction. I pick it up, and then I image my fringes on the camera. It's a small. So what does this instrument allow me to do? Oh, let's see. Well, because it's my instrument, I can change the field of view, resolving power, bandpass as I wish. And it's not that hard. I have rotation stages, I have my mirrors, I have my aperture, I can change things, and I'm actually working with a few students that we're working on computerizing, because everything in my instrument is manual. And by that, I mean everything is manual. If I want to take flats, I go there, I put a card in front of the one arm, and then I go back, take my image. If I want the other flat, I'll go there, take this card, put it in the other side. That's how manual everything is. And if I want to change between calibration and sky, I have to go there, take the calibration setup out, put the other things in. So it's in the progress and advancement stage. But you can see here, I can go, depending on what kind of, the G is the grooves per millimeter on my grating. The resolving powers, I can go anywhere from 10,000 to more than 150,000 resolving power. And then I'll note this, the field of view and resolving power on my system. So I said in grating spectrometers, the field of view and resolving power, they're like this. If you take the field of view high, the resolving power drops. In my system is similar, but they're in a different level. So the field of view, if you take the field of view higher, the resolving power still drops, but it drops in a different level. It was 170,000, now it's 130,000. Or it was 130,000, now it's 170,000. So it is still that little bit of game over there, but in a different level. So just imagine of how much things we can do on comets or in planetary atmospheres if we can get about 48,000 resolving power over 40 arcseconds field of view. The other beauty thing about this instrument is SHS instruments don't need a telescope, period. I can literally take the instrument, look at the sky, and I would get 100,000 resolving power over half a degree field of view. I don't need a telescope. They can be sent to space without a telescope. But we would like to couple them to the telescope if we want to decrease the field of view to match our target. We don't need a wider field of view if our target is smaller, because it's just going to add noise to our data. So you can see the numbers in here. The SHS input acceptance angle is the angle, the field of view angle of the instrument if I would use no telescope at all. This is how wide I can go. But because I'm coupled to the 60 centimeter telescope, in here, I can go to a smaller field of view. And then if I couple it to the 3-meter telescope, I can go to the smaller field of view, conserving the resolving power. Now, the people who do data reduction pipeline might appreciate this part because I keep the resolving power same. I don't need to play with different resolving powers. The red row is what I currently have at Lick. I'm optimized on that setting. About 48,000 resolving power on 40 arcseconds field of view. So here's the beauty of the Lick. Do I have 2 telescopes at Lick? Sure I do. How many other places have this? I know none. These 2 telescopes share a focus together. So technically, my current system uses the 60 centimeter auxiliary telescope, but I can use the same focus and at one night switch to the different telescope and look at the different field of view on the same target. So I'm having this, oh, I like this, and then go back, come back, go back, come back. See if it's homogeneous, not homogeneous. There's so many different science that can be done with these techniques. They're jets, they're, how things change. So if I decide to use a 3-meter telescope, then I have to put the focus of the both telescopes in the shared focus plan, and then I have a coupling system to the both telescopes, an extra step for the coupling system. And then it goes through my instrument and does its all usual game. So the pictures I showed, if I wanted to use a 3-meter telescope, a little bit of history, I actually started with that part. I started saying, I'm not gonna, not use of this advantage. I'm gonna use both telescopes. And I spent 2 years doing it. And then I did it. I coupled to both telescopes, but then I had huge vibrations in my system. I had enough vibrations that, I spent about 8 months. That 3 or 4 inches on the screen, it was 8 or 9 months of time to go from this fringes in here to this fringes in here. Because the vibration is killing my fringes. And then it just turned out, because I had those coupling system over there, when I was taking data, the 3-meter dome was rotating, and it was just shaking my entire world, my entire tiny world. So I decided, okay, I'm gonna, it would be a good idea to finish my PhD at some point. So I went back and I kind of said, okay, I'll go with the 60 centimeter telescope for now. And I was very lucky that nobody knew that the focus of the 60 centimeter telescope can actually come down that far. Even Steve Wood didn't know. People who built it didn't know. They were just like, we were all surprised. It was a very lucky thing. But we brought the focus down, and it was still coming down. It was coming down. It was coming down. It came down more than 4 meters. and then we were making sure the secondary mirror would not fall onto the primary mirror. And then there it was. It just came down enough that it reached my instrument. So where the instrument is, I did the optical design. Optical design is, I can't say it's finished, but it's the version that I'm very comfortable with it. The mechanical design is the version that I'm very comfortable with it. The vibrations are taken care of. The temperature changes have been studied. Drift in the mounts have been taken care of. The instrument is basically stable for getting data, and I am getting data. But what's remaining is a good understanding of my data reduction pipeline and calibration. And this is what I'm working on right now. Because what happened is I started getting data. And then I was like, oh, these are cute data. They're fringes. Now I have to build a data reduction pipeline to reduce them. And then I did. And then there were some understanding that needed to go into understanding how these data are evolving with my system over there. Now by system, I have to say it's not the instrument anymore. It's the combination of the instrument and the telescope. So with any Fourier Transform Spectrometers or with any interferometers, you can say, or I can say, how hard this can be. I have some fringes. I Fourier transform the fringes, blah. I have power spectra. And then I have, boom, a power spectra. That's it, yeah? Well, let's see. So yes, I have some fringes. This is my white lamp or my calibration lamp behind my field of view stuff. If I just put the lamp after the telescope, before the instrument, it's as simple as I said. I have some fringes, and then I get this gorgeous power spectra, and then I get my data. But my targets are not inside the pool, they're in the sky. So they have to say hello to the telescope before saying hello to my instrument, which is a Cassegrain telescope. How complicated that can make it. Everybody uses Cassegrain telescope. They're everywhere. I had a Cassegrain telescope for my birthday, my second telescope. So I put the lamp outside. It's a neon lamp. I was only looking at the laser line. It came in, because I'm not focused on the sky, I see the signature. I see this Cassegrain mirror, the spider pattern, right in the middle of my fringes. It's the shadow in the middle of my fringes. Now, this is only one wavelength that you can see it. Imagine if I have many emission lines. For every emission line, I'm going to have a different shadow because I'm diffracting the shadow as if I'm diffracting the light. What it does, it blurs everything. What that blur does, it messes up my Fourier transform. So I get all these lines that if I'm not careful, they're just because of the Fourier transform error of those spiders. Okay, so this was me a couple months ago. And I was like, God, what can I do with this? Well, I'm still figuring that out. So, but good news, I have really good candidates. It turns out people have been using some techniques and so many different places, not in, because nobody uses interferometers with Cassegrain telescopes. They don't use these things. Nobody is focused in some random place in the middle of their instruments. People are usually nice. They're focused on the sky or they're focused on primary mirror and they don't see the spider. So that's one thing I'm still working on. But the other thing I promised you was about the tuning between the wavelengths. So here's a very nice thing that I did for my own amusement, and it just turned out beautiful. So I'm looking at the sodium D lines. So these sodium D lines, they're famous, they're everywhere. This is my data from sodium D line. Again, remember, this sodium hollow cathode lamp is after the telescope, before my instrument, is before the field of view stop of my instrument. So you see both sodium D power spectra over there, and by Fourier transforming it, I get both sodium D lines. And you see how separate those both sodium D lines are. That's just gorgeous, because you can see about 48,000 resolving power, 5.97 angstroms is just spread wide apart from each other. There's a lot of science that can be done with this kind of sensitivity. And for the tuning part, so here at this picture, I am tuned far away at D1. And then I'm bringing D1 in. You can see there's only one D1. There's no signature of the D2. It's coming in. And then, and then also both of these are same thing, because when you're doing a two-dimensional Fourier transform, it's just repeating itself down. So the wavelength, if it's to the right at the top, it's to the left and the bottom. So they're basically the same lines. So we have one sodium line, and I'm slowly bringing the second D line. You see, the other one is just here. That's so cool. And then this is the other one. It's coming in. Now you can see both fringes in here. And then we have both sodium lines. And then I'm tuning past the D2. So the tuning is also under investigation. And if I do all of these, do the calibration, the tuning, everything, this is where the instrument is and would be. With SHS, with Khayyam on CAT and Shane, the Khayyam's étendue is 650 It's a high sensitive instrument. But what it doesn't like to do, it doesn't like to look at tiny things. If you're looking at small targets in the sky, SHS is not happy with that because it has wide field of view. It depends on how small you can go. But you put it in perspective of Keck, it's about 47,000 resolving power with the étendue of 440. And SOFIN is about 8 étendue, which is a great instrument, but it's low sensitive. It does what it's supposed to do. And also the Coudé spectrograph at Tunable Observatory. So this is how my instrument compares to the other instruments. And what I like to do with it? Well, here's an example that I've been interested in a while. Looking at the night side, the night emission lines on Venus. So looking at this field of views, I'm just saying, I can actually match my field of view at the resolving power. This is a hypothetical project, by the way, because I have to deal with that huge intensity contrast first. But if that's taken care of, I can match my field of view and use, if I use the 3-meter telescope and the 60-centimeter telescope, I can go and match it to the dark side of the Venus. And look at 74,000 resolving power, 111,000 resolving power, 95,000 resolving power at 55 arcsecond field of view. We couldn't do these things before. I'm not saying it's good or bad. We just couldn't do these things before. And my most favorite thing to do is this one. Now imagine a comet coming into the solar system. Well, we all know the comets, as they get closer to the sun, they get more active. And they come out just, all these volatiles coming out. It enlarges. What if I had an instrument? Well, I'm not saying that anymore. SHS, Khayyam, can look at this coma at 18, half a degree field of view on about 96,000 or 9,000 resolving power. Simply if I change the beam of it on my grating, under my grating to 1,200 grooves per millimeter. And then I can, on the same instrument, I can change it using a different telescope to look at a smaller piece of the comet. I can go and change my field of view. If it's further, I could have actually matched it to the comas that I wanted. And if it was extremely far, I can use a larger aperture telescope to get more photons, but I still have a larger field of view to match to my coma at that distance. Well, let's remember, Khayyam is an interferometer, so I don't have any imaging information in my data. I get one integrated spectra over my field of view. But I can get a spectra from this field of view, and then a spectra from this field of view, subtract them from each other, and I'll get the information in between. So there's so many interferometry games that we can play to get some kind of spatial information. And then Khayyam can do this when it's compact. It's a really good, in my opinion, it's a really good candidate for space missions. It can be a high resolving power in a space platform, finally. Okay, so I told you about my instrument, I told you about what I want to do. I'll leave you with some memories of my life living and working at Lick Observatory, Mount Hamilton, last 4 years. Thank you so much.
Okay, if you have questions for Sona, put your hand up and I'll come around to you. Sona, I'll ask the first question.
Yes.
So, what range of visible near infrared? What ranges are you sensitive to?
I am actually working on optical wavelengths right now. Mm-hmm. So I am between 400 to 700 nanometers. Currently, I'm actually my bandpass is about 130 angstroms. and that's around either sodium lines or oxygen green line or the red line. But if I want to tune, it just depends on how much the coding of the mirrors over there is. So I want to say roughly between 380 or 700 to 700 nanometers. But the technique itself, I can go to IR as well. And my advisor, he worked on a rocket mission that was launched a couple of weeks ago. That was in UV, and he is interested in going to extreme UV. So yeah, the point is, because this is an all reflective design, it has no bandpass limitation in the technique. Like with microscope interferometers, that's not true. You have the beam splitter over there. You have a transmitting optic, but not on this one. Yes?
Yes, you call your instrument a Spatial Heterodyne Spectrometer.
That's true.
And my remembrance of interferometry with heterodyning is that there's a frequency offset, a shifting.
Well, I
didn't see that.
I didn't name this instrument. Someone else named it. Fred Rissler and John Hollander, and So this is I have this conversation almost in every meeting that I go. It's a spatial heterodyne spectrometer, but don't believe that. It's a spatial homodyne interferometer.
Homodyne, yeah, right.
So, yeah.
Okay,
sorry.
I just thought maybe I misunderstood.
No, you did not.
Thank you.
I would change the name, but I'm just too young to do it yet. So.
Other questions?
Any other questions? Yes.
So the Coudé Auxiliary Telescope is still working?
Yes, I am until 2 weeks ago.
Okay, because I used it years ago. I wasn't aware that it was still working.
Oh no, well, it has lots of technical problems, but I'm kind of learning on how. So it breaks, and the astronomer staffs over there are very kind. They come and we fix it every night. But it's a smallest aperture on the telescope, so it has the least priority on the mountain as well. But it is still, if you have used it, so the entire telescope, for reference of others, it's not connected to the computers. I have one pedal that has west, east, north, and south, and then 2 buttons that I can go faster or slower. And that's what I know from the telescope. And
because you also get image rotation there.
yes, well, I don't care,
Yeah.
because I get one integrated spectra over my field of view. Thank you. That's another reason why this instrument is really cool.
So what now? You're going to get your PhD in a few months, and your instrument's working.
Yes.
What's going to happen next?
Okay. Well, I have been thinking about my PhD project since I was 13 years old. I literally have a notebook that I would say, I'm going to do these things. And I actually done most of those things because I wanted to get myself into trouble. It's funny, one of the things that I wrote in notebook is I want to be so cold in the observatory that my fingers actually turn purple, and it did. So when I did that and I'm here, I obviously think about what's next, and I've been thinking about it when I started this project. My vision is, for my career, I wanted to design this instrument, build it, get data. Get data, improve the instrument, get more data. Improve the instrument, get data. Like when I envision myself when I'm 60 years old, I like to look at my data and say, oh, this is because of the science, and this is because of the instrument. It's hard to say that. And only there's one way to do it for a very long time and do it really good and do everything yourself. So that's what I want to do. I really want to continue working on this technique and bring a new approach on planetary science studies, looking at high resolving power at wide field of view. The other good thing about this instrument is it works with the small telescopes. I can take a 1 meter telescope and turn it to a gigantic high sensitivity apparatus for all planetary sciences to use. So I just don't want to go and, because one thing that it's not a secret to anyone is we are in some kind of budget crisis and, some kind of funding, and then using large aperture telescopes, 10 meter telescopes are getting more and more competitive. So if I have my hands on something that I can use a small telescope and get high resolving power spectra, that I can do high sensitivity studies on it, I want to work on it and just give it life to this vision, to use 1 meter telescopes all over the world and nation on nightly basis. So if one person wants to study a comet every night, we can do it because it's relatively much cheaper and relatively achievable. This is practical, but it's also new too. So I'm not walking on a path that other people have walked on it. I'm literally making a path. And yeah, it's hard, but I'm very much happy that I'm doing this. So that's next. How I'm gonna do it, I have no idea, but I'm gonna do it. I can't say I have no idea. There are options. There are many options. But I'm still deciding which one to pick. Thank you.
Okay. Sona, if you have any more questions, please feel free to come up and talk to Sona after this. Sona, we have a special SETI Talks mug. I'm sure that you can use it with some caffeinated beverage at late nights and Lick to work through some of those remaining problems with and speedily get through your PhD.
Thank you.
Please join me in thanking Sona for a great talk.
Thank you so much.